Welcome back, welcome back. We see now that, again, dealing with the tensor stuff and the notation thereof, we have to be pretty careful with understanding what is preserved and what isn't. So that's what this question's for. Prove that the symmetry or antisymmetry of a tensor is preserved by Lorentz transformation. That is, if T mu nu is symmetric, show that T bar mu nu is also symmetric. And likewise for antisymmetric. Alright, so let's understand that the transformation notation and symmetry conditions are T bar mu nu is the transformation matrix of mu and lambda, transformation matrix nu and sigma, summed over lambda sigma, and then it gives us the mu and nu left over. Symmetry says that the bar has to be the same before, or excuse me, symmetric is that if we switch the ordinates here or the indices, that we get the same thing. Antisymmetric is if we switch it, it's at the cost of a minus sign. So now we have to show that that's preserved in the transformation of the Lorentz transformation. All right, so here is the general setup that we're going to have to do. If we let T of mu nu equal plus or minus nu mu, plus for symmetric clearly, and minus for antisymmetric, what we need to know then is that we have to show that the transformation of the T before and after gives us the same thing. So we have T bar is equal to plus or minus the T bar of nu mu, where we switch the indices. So let's define that we know that T bar is equal to these two transformation matrices acting on T lambda sigma. Let's then show here that if we have these in red, we're summing over those, okay? So the goal here is to show that because we're summing over lambda and sigma, those are considered dummy variables. Okay, so we can switch the dummy variables without any ordinates of worry here. Because so long as we, if we switch both of them, we see that lambda first, sigma first, or sigma second, first, second, they're still dummy. They don't take anything. They just prescribe a value to attain that we have 0, 0, 1, 1, whatever. They're just dummy. They don't actually mean anything for the totality of the fact that the end result is a nu mu. So we have to have a nu mu here. Those stay unchanged. Okay. The dummy variable argument is used all the time. Again, maybe not the best in terms of pure analysis work, but I've seen it a lot in many multitude of physics classes. That being said, because lambda and sigma are both summed from 0 to 3, it doesn't matter which we call lambda and which we call sigma. Therefore, by switching the order, we see that we get lambda or T bar of nu mu is equal to lambda and the sigma nu and lambda of the mu lambda, little lambda of T sigma lambda. I color coordinated it as best as I could because if we switch the transformation sides, we have to switch the T order as well because multiplication is not commutative. So we switch it here. Again, the color coding there is to help you there. But what this shows is that we get exactly what we thought we were going to get when switching it. So we get the plus or minus transacting through, and then we see that we get the plus or minus here after the fact, and we could switch it back because lambda and sigma are dummy variables. So we successfully switched the mu and nu, and therefore we could bring into the account that we were able to successfully switch them while bringing in a plus or minus there. But we know that this form in the purple, which is what we showed here in the green and red, just a little more nicely color coordinated. The purple one is exactly what we defined earlier in the T-bar notation. So we're good to go. I mean, I think that these things become a little easier to see after some practice with them all. But this thing is having this as a property is almost required in this sense because we have to use things that are preserved and invariant in systems like the four vectors and things of that nature. Again, other classes can go much more in depth on this, any relativity class will. But this being said, the tensors, getting used to them and their properties, well worth the investment.